Hi everybody, and welcome to lecture number 3 on game design theory. This is Rob Zubek, and the class is CS377 Game Development Studio at Northwestern University. So in this lecture we're going to look specifically at systems and gameplay, two interrelated and central concepts in the modeling we've been developing so far. If we look back at the previous lectures, we've been developing this model for understanding game design and understanding games that splits the overall game design into three levels, three layers, as it were. At the very top level, we have player experience, so the sheer enjoyment of the game, analyzing what it is about the game that creates a specific feeling for the player, that creates some kind of an experience, and how that maps to the player's own motivations and what it is about this experience that is what we call fun. Then on the very low material level, we've been talking about mechanics. These are the material items, the cards, the pieces, tokens, rules, or more generally speaking, the objects, the verbs, and the rules of combining them that form the material game, the artifact, the thing we put in a box, or the binary that we upload to an online store for the players to download and interact with. But neither of these is enough by itself, right? Because experience doesn't come out of nowhere. And also, just describing the cards and the chips and the rules doesn't really tell us what the game is like to play. The missing link is the gameplay. The missing link is the what happens when those pieces, the objects, get picked up by the player and the player starts playing the game, and the behavior of the players and the game as it responds to its rules, how that develops and unfolds over time, and how those activities and those patterns of gameplay turn into the player experience that the player finds enjoyable. So we've been talking about player experience as something that we as designers are striving to create, that sort of feeling of fun, whether it's through challenges or giving the player something to strategize about, or maybe just a casual experience where they're just having fun and not worrying about things. Whatever it is that players want out of their game, it is something that we need to think about how to create, how to bring it about. And the problem is that we can't create this directly, right? We can't create the feeling of enjoyment for the player. All we can do is set up mechanics and set up game elements that will eventually bring it about when the player is actually interacting with this. It's this sort of second order design problem that we've talked about. And mechanics are very material, right? These are the objects, the actions, the rules, or to use the language metaphor, the nouns and the verbs of the game and the grammar that binds them together. A structural analysis of a game, looking at purely mechanics, will tell us what the pieces are, but it doesn't necessarily tell us how the game is going to play out. And for that, we need to take a more dynamic look at the game evolving over time as the player interacts with it. So this is going to be the focus of today. So in this video, we're going to continue our discussion from mechanics, looking at mechanics such as resources and units and so on, and how they come together to form feedback loops, and how that illuminates systems that are going to be arising out of the combination of these mechanics. In the next video, we're going to talk about something slightly different, which are activity loops and progression, which is going to illuminate gameplay. So let's start with the first one. So in the previous discussion of mechanics, we've been taking a very static look at things. We've looked at the objects and the actions and the rules that combine them. But what we need to do now is take the next step of looking at how does this turn into behavior at runtime, as it were. How does this turn into behavior that evolves over time? One aspect of it is going to be that players are going to be picking up the pieces of the game and acting within the rules and changing the state of the game world as they play. And also they are going to change their own behavior as they play, as they figure out the rules of the game and different strategies to win. So discussing how the game unfolds over time is going to require some kind of a conceptual structure from us. How do we understand this evolution? How do we understand how a material set of game elements, of mechanics, is going to turn into runtime behavior? To this effect, we're going to take a cybernetic approach for looking at the evolution of the player and game behavior. By cybernetic, we mean we're going to look at players and the game as two parts of an ecosystem of sorts. They're two elements that affect each other all the time, and it is through the sort of give and take between the player and the game's rules that we're going to see the behavior of the game evolve. Cybernetics is a very interesting historical field. It is the field that basically gave rise to computer science, and its history is very interesting. Norbert Weiner's work on cybernetics and control systems is widely credited to be foundational in this regard. This is not necessarily the right lecture to be talking about cybernetics, but I would encourage you to find out more about this because it is a very interesting, if historically interesting field. But what we mean specifically here is that we're going to look at the combination of players and the game as kind of like a state machine that evolves over time, right? We're going to look at them together as intertwined. And at any given moment in time, both the player and the game are in a particular state. The game is in the state in the sense that the particular pieces are in particular position, maybe they're moving with a particular velocity and momentum and so on, and the player's mental model is also in a particular state. They're thinking about something, they're going to analyze what's happening, and then the players are going to perform some actions on the world. Players are going to perform some actions on each other. Maybe they're going to bet against each other or attack or whatever. And most interestingly, the game world also acts because the game world is governed by rules. So what players do will have an effect, and the game rules will respond to that possibly. It doesn't have to be through an AI, right? It can be through just the rules of the game causing some change to happen. And then that switches the game from one state to the next and to the next. And we can talk about the development of the game as transitioning through a variety of different states, depending on which actions players take. But even though we looked at the state space diagrammed as a chain, it might be more illuminating to look at it as a loop, because these states and actions form a feedback cycle. States are something that will affect the players and the game responding to it, and those actions will then come back and affect the state again, and they form a cycle of sorts, kind of like this, right, where the inputs so imagine that the function is a representation of the player or the rule set. It is something that will transform inputs to outputs. The inputs are the state of the world, and the function creates some kind of a change, some kind of an action that will then go and affect the state of the world, thus changing the inputs into the function on the next time step, as it were. This is the kind of a model that was introduced in the early cybernetics work, and the leading example used in this kind of work is that of a thermostat. This is probably the prototypical example of a feedback loop. So a thermostat, let's assume we're talking about just air conditioning, right? Is something that is monitoring the temperature of the room, and if it goes too high, it turns air conditioning on. So as the state of the room, the temperature increases all by itself over time, at some point the thermostat or the agent is going to turn on, create an action of cooling the room, which is going to affect the state, forcing the temperature back down, which is going to at some point affect the function or the agent again, and it's going to turn air conditioning back off, which is going to allow the state of the room to either remain the same or maybe keep going back up slowly. So this is an example of a negative feedback loop. What we mean by negative is that it takes the difference between some kind of a desired state. So we can consider of the function or of the thermostat as something that has a set point that it's trying to reach. And it's looking at the difference between the set point and the current state of the world, and it's trying to minimize the difference. So at some point when the difference becomes too large, it's engaging in an action to reduce this difference. Turns AC on, which will push the temperature back down. It's negative feedback loop because it's trying to minimize this difference. It's also considered a self-correcting feedback loop. But there's a flip side to this. We could also talk about a positive feedback loop. Now, a positive feedback loop is something that's going to take a difference and try to magnify it. It doesn't have to be intentional. So imagine that the AC was broken, and instead of the thermostat turning on air conditioning, it would turn on heat with a strength proportional to the difference, right? So if the temperature rose above the set point, it would notice the difference and turn on the heat proportional to that, which would amplify the effect. It would cause the temperature of the room to grow larger, higher, which would turn the heat even higher, and so on and so forth, forming this always increasing curve that departs away from the set point. That's what we mean by positive feedback. The difference from a desired state keeps increasing. We talk about the desired state, but it doesn't have to be an intentional desired state. It's just the state of the system. And positive feedback loops in that sense are very, very, very common in games and also in reality. So your stereotypical example is compound interest, right? You imagine a world where interest rates are not 0%. And if we put money into an account, it's going to gain, let's say, 1% in the first year, but then this interest is going to be deposited back into the account. So on the second year, we get 1% again, but it's 1% of a larger amount. And it keeps going and going and going, and it turns into a superlinear curve over a very long period of time. And so it is with interest, with reinvestment. These kinds of feedback loops are very commonly seen in games centered around resource extraction and resource production, as we will see in a few slides. But these things don't have to be quite so simple, right? We can now that we have the basic model of inputs and outputs and a feedback loop, we can start making them more complex. Imagine a thermostat that controls both air conditioning and heat, and depending on how exactly the different set points for those two different elements are set up, it could be fighting with itself, right? It could be trying to turn heat on, which will trigger AC, which will turn it back down, and so on. Like, these control systems can get very intricate and also kind of hard to tune. And there is an entire art and science to designing control systems in a way that makes them work correctly. And of course, we don't have to talk about a single entity, because in any kind of whether it's game or an ecosystem or whatever, there are going to be a large number of these entities all monitoring the world state, all creating actions, and those actions will change the world state not just for them, but for everybody else as well. So a classic example would be that of two different populations which form which affect each other, right? So they will be interdependent feedback loops. The classic example is, for example, populations of predators and prey. Let's say foxes and rabbits, where the population of rabbits, as it grows, creates a food source for the foxes, and so the population of foxes grows with it, up until a sort of breaking point where the population of foxes is too large to be supported by the population of rabbits. Basically, rabbits get hunted out of existence, and that causes the population of foxes to drop back down. This kind of a mutual feedback loop is a classic prey and the predator and prey model. But it doesn't occur in just those cases, right? Any kind of system where there is a production and consumption will be following these sort of mutual feedback cycles, and the economical analysis of production and manufacturing and consumption is a prime example of this. Analysis of production chains, of analysis of how different kinds of manufacturing elements come together and to produce an end product is a great example of these mutual feedback loops. For example, when we have a production chain, a snag at any point will change the state of the entire situation for everybody else downstream, which will cause ripple effects and will cause them to have shortages or have oversupply, and it will cause them to react in unexpected ways, as we have seen in various supply chain problems throughout history. So using feedback loops is a very useful way of looking at an evolving game state. So even though we draw this as a linear diagram, we can consider a game as a collection of feedback loops that all evolve together. Loops that take game state at some particular time, player actions, AI actions, game rules cause this game state to keep changing, which then changes the actions, which then changes game state, and so on and so forth. And we will look at positive and negative feedback loops in 1 second, and a little bit later we're going to look at how loops of different frequencies affect each other. Probably the most common example of feedback loops in game design is the game of Monopoly. Every designer's favorite dead horse to beat up on. The reason for this is that the feedback loops in Monopoly are so exaggerated that it's really easy to talk about them. So, as you remember from Monopoly, players use random rolls to walk around the game board. They buy up properties, and if they land on somebody else's property, they have to pay rent. And what happens is that as somebody buys up a bunch of properties with their money, it increases the chances that everybody else will land on their properties, and also decreases the chance that they will themselves land on somebody else's property, which generates money in two ways, either by income from other players or by reducing expenses. So what happens is that players who have a lot of money and a lot of properties will end up with even more money and even more properties over time, and vice versa. Players who had bad luck and were not able to buy properties, they will be faced with increasing chances of landing on somebody else's land and paying more than they're bringing in, which will result in a kind of a spiral and very slowly hemorrhaging money, as it were, over time. This leads to that very well-known gameplay of Monopoly where within the first hour or so you kind of know how things are going to turn out, and barring very unexpected die rolls, you can kind of see how it's going to develop over the remainder of the game. So this kind of positive feedback might look questionable, but it's only looking questionable because it's not balanced by anything. The positive feedback is something that happens in a lot of games where it's a little bit more balanced. Examples like StarCraft for real-time strategy games, or Civilization for turn-based strategy games, and so on, are full of these positive feedback loops, where building some kind of units or buildings will end up generating more resources, will let you produce more units, more buildings, and so on. And there is a variety of different methods for balancing this to make sure that this production does not spiral out of control. But positive feedback does have some effects. It causes early successes to count the most, but because the results of those early successes will compound. And because of that, early winners might get entrenched. This is not so much a problem in a single-player game like Civilization, when played single-player, for example, but it is a problem in multiplayer game, because we don't want the feeling of early players getting entrenched. We don't want the player to think that they no longer have any hope for winning. As for negative feedback, that also exists in the game. So if you remember, negative feedback is the one that's trying to minimize differences. Mario Kart rubber banding is the prototypical example. Basically, if the human player was doing poorly against the AI, they would start getting random drops that help them. And if they're doing really well against the AI, they might getting affected negatively more than average, thus causing the player to catch up more quickly if they're behind, and also maybe fall back if they're way ahead. This can be, again, if it's done in a balanced way, it can really make the game feel more interesting, because you're going to be always in the middle of things as opposed to far ahead or far behind. However, it also causes the feeling that late successes count more than early successes, because the early successes are going to get pulled back, reined back in, and late successes will not be reacted to. In a certain sense, early wins are not as rewarded as late wins. And if the player knows about rubber banding, that's going to make them feel negatively about it. That's going to make them feel like the game's not really appreciating their effort that they're putting in, or that it's actively hampering the effort. So the challenge is always going to be to mix them together, to have both enable positive feedback, but also not let it go completely off the rails, and maybe help the player a little bit if they're falling behind, but not in such a way that's really obvious what's happening and derailing their enjoyment. And this is how we can start considering how we might fix a game such as Monopoly. When the problem is the positive feedback loop of too much money producing too many properties, producing even more money, maybe we can add friction there. We could reduce the amount of money that's being collected, or we could introduce taxes or some other form of basically friction in the feedback loop. And similarly, in the loop that causes people who have less to lose whatever they have, we could help them by adding, for example, extra elements in the game that will help them a little bit, or adding elements that will cause players who are winning to not win as quickly, or to lose some of the resources. So let's look at some more concrete examples of feedback loops. And in these examples, we're going to concentrate specifically on resource feedback loops, because that's a great example. The resource mechanics are very popular in games, as we've talked about before, and it's going to be very clear to see how feedback loops such as an economy work. So a great example are dungeon crawlers such as Diablo. In a game like this, the basic activity loop is around venturing out of camp, finding and hunting or fighting with various enemies. When you vanquish them, they will drop loot. They will drop items, they will drop gold, which you can collect. At some point, it will become too much to carry, so you return to camp, collect all this inventory and sell it off for gold, or use it to equip your own characters. But the gold that you gain from selling it, you can use to buy weapons, fix up weapons, get armor, buy spells, learn skills, etc., etc. And then once you're rejuvenated and once you've upgraded your characters, your weapons, and so on, you can now venture out. And as you venture out, you can, because you have improved your team, you can go and venture into further areas of the game, face tougher challenges, and because of that, get more loot, get better loot to equip yourself, to sell for even more gold, and venture into even better areas, and so on. We can look at the resource loop in a very schematic way, right? Hunting is something that consumes our health. It consumes consumable resources such as arrows or other such, maybe potions. But it's something that if we put work into it, it gives us loot. And this loot is something we can come back to camp and sell in exchange for currency such as gold. And then as we restock and recuperate, we convert this gold back into either consumable things like potions and arrows, or maybe we buy more armor, etc. This kind of a resource loop describes how these resources are converted. The conversion is not free. At each point in the state space, we have to put in work in order to make that happen. However, you can see that depending on how the numbers work out, this resource conversion can become pretty profitable. RPGs specifically are full of these kinds of resource conversions, but other games as well. And one interesting thing about resource conversion is that it makes all of these resources have value in the context of each other, right? So if killing monsters gives you gold, and gold gives you weapons, and weapons give you more monsters, in a certain sense, these are all interconvertible, right? Monsters end up having a cash value, or monsters can be considered as having weapon value, right? Like you can take X monsters and convert them into Y weapons. Basically, all these things turn into currencies, and you have to, as a player, you're working all these loops to make sure you get a good reward out of your actions. As a designer, you have to make sure that these feedback loops are tuned correctly and they don't behave badly. What do we mean by badly behaving conversion loops? Let's take an example of Pokemon Hunter. So, this is a game that does not exist because the IP holders, I'm sure, would not allow for this. But imagine that you go out hunting Pokemon. And each Pikachu that you find takes 10 bullets to kill on average. And each Pikachu pelt is worth 50 gold points. And each bullet is costing you 10 gold points. And this is a very morbid example. But what does this tell you, right? If we do the math on this, we will see very easily that it's not worth to go hunting Pikachu, because you will use a lot of gold to buy all these bullets, but you're not going to get a lot of reward out of this, just because the tuning numbers are just don't make sense. However, if we as designers were to retune this so that it takes only one bullet on average to hunt an individual, and then we get 50 gold out of that, then these tuning values are much different, right? Now the hunting party is going to earn a lot of money because their revenues from their actions are much higher than their expenses. And we also, as designers, need to think about what happens when we take this to an extreme, right? If we have a forest full of these individuals, if there's an infinite population of them and they keep respawning, this kind of a resource loop turns into an infinite source of money, right? If the tuning values in the sell part are so high, or maybe the cost values in the hunt part are so low, that it generates a really high return, then the players can keep churning through this loop over and over and over again and amass huge amounts of resources. So this is one of our goals as designers, to keep a careful eye on the tuning values and make sure that they are balanced. And we don't have to balance them necessarily in just a single loop, because remember, all these resources are going to be participating in a larger ecosystem, right? So with gold, you don't just buy weapons, you can also buy all sorts of other things. So by adding a lot of different sinks for resources, we can ensure that a surplus is going to get drained away towards other uses. And we can also, by adding friction into those loops, by adding time spent or some other kind of an element that's going to discourage player from participating in them, we can encourage the player to participate in a number of different activities instead of keeping churning through the same loop over and over again. So we talked about gold participating in a number of different resource conversion loops, but in fact it's not limited to resources. Mechanics in general will participate in a number of different interactions with each other in different kinds of ways. So in a game like Diablo, we have a large number of mechanics, and at some point it becomes easier to talk about not the individual mechanics, but rather the collective systems in which they participate. So what we mean specifically is that something like loot and armor and gold all participate together in an inventory system, right? An inventory system would be something that describes how what happens when we pick up loot, how it's going to interact with each other in terms of capacity and carrying weight. It's something that allows us to bring it back to camp and either equip it or sell it. And as we talk about selling it, we can start describing the economy. The gold that we get out of this is a currency, and with gold we can do a number of different things. We can sell items, we can buy items, we can buy spells, materials, upgrades, and so on. And that, in turn, participates in a crafting system. So a crafting system might be something that describes how different NPCs or maybe the player character is able to convert some materials into some other materials, and then those materials can participate in the economy and be bought and sold, or they can participate in combat. If the player is crafting items or buying those items, they can turn them into weapons, or maybe they can turn them into armor or magical items, and then use them in combat in order to increase their chances of winning, which will then impact inventory because you will be able to get better stuff, better loot, sell them for more gold, and so on. We can consider these systems as collections of mechanics set up in a specific way. They do not contain mechanics themselves, right? Mechanics are going to be shared between different systems, but a system is a setup of how they work together in a specific way. So, for example, combat is going to describe how different kinds of mechanics and resources, the objects and the verbs, work together in combat, in encounters between different kinds of entities, and determining who wins and what the results are. Compared to something like the economy, which might be using the same objects, such as loot items and gold, but it's describing different kinds of interactions. It describes how they can be exchanged for each other at specific stores, specific places, and what are the exchange rates between them. When we design game systems, we want them to be interlocking. We want them to be sharing as many mechanics as possible because that makes it interesting. By having a system such as economy, which where the mechanics of gold and loot and crafting materials interact with basically everything else, it makes economy an interesting element in the game to interact with. When players do things, it will affect their economic situation, and it will, because it's pulling in the other systems, it's going to affect other systems as well. It creates this interesting tension where every time you interact with a system, it pulls on the other systems. So you're always in this dynamically stable situation of things are never static, and you're trying to keep all the plates spinning. You're trying to keep all the systems working together well. Finally, systems let us, as designers, consider game design using slightly larger blocks than mechanics. Because if we start designing the game from mechanics, as we've seen, they are shared in between different kinds of activities in very different ways. It can be fairly challenging to start game design from the mechanics level. It often is easier to start from the systems level because then we have larger building blocks, as it were, and we can figure out how they fit together, and then we can go back and figure out the individual mechanics that are going to make them work. This is something that might be more common in the design of larger games, not necessarily smaller games like game jam games or student games, but it is something that does help in the sort of structuring a larger gameplay system using these systems as a building block. So as we analyze games, we can look at the individual mechanics, and that is the sort of most immediate thing we can see in the game, right? We can see what the game objects are, we can see what the actions are. But then naturally we will start looking at what do they build together in forms of in terms of how they form systems, how they form idiomatic combinations that work together, and how does this impact gameplay over time. And system behavior is really hard to predict without playtesting. Systems are notorious for acting in unpredictable ways, and in computer games, they are typically complex enough that it is impossible to analyze them analytically to form to create closed form equations for how they're going to act over time. It's really a matter of implementing basic versions and playtesting them either in person or running simulations, for example, in order to see how they actually behave. However, because of their complexity, they are also a fascinating challenge for the player and something that players enjoy interacting with. So in this video, we've talked about resources and feedback loops and how they together they interact with each other in idiomatic ways to form systems. And in the next video, we're going to take a slightly different look at activities and what players do over time and progression through the game. See you there.